Okay, so let's understand question 13 first. Okay. So just go through the question. Yeah, so I'll just explain the question first. And so it says a simple pendulum is suspended from the ceiling of a car, taking a turn of radius 10 meters at a speed of 36 kph. Find the angle made by the string of the pendulum with the vertical if the angle does not change during this turn. So basically, what it means to say that the angle does not change with respect to the turn is that the pendulum with the bob of the pendulum or the particle attached at the bottom is in equilibrium. That's why the angle is not changing, but it's in equilibrium with respect to the frame of the car. And the car is taking a circular turn, so it happens to be at a uniform speed, so it happens to be a uniformly rotating frame. So in that frame, when we describe the equilibrium of the bob of the pendulum, it should include the pseudo force, which in this case is the centrifugal force. Okay, so let's apply that concept and understand how to solve the question. So basically, if you look at the top view, you're not really seeing the pendulum that much because it's attached to the ceiling of the car, but you understand that the vehicle is in a circular track like this, going at a certain uniform speed v, and the radius of the circle is given to us. So the radius and the speed of the car is known. Now inside the car, when you look at the side view, so you notice that there is a pendulum which is suspended. Now it will get some angle with respect to the vertical because the car is in. Okay, so in the rotating frame of the car, okay, this pendulum will be in equilibrium under the action of, or the bob of the pendulum is in equilibrium under the action of centrifugal force, weight, and tension in the thread. Okay. So to draw a more detailed diagram, the thread will be at an angle theta like this with respect to the vertical because of the action of centrifugal force acting radially outwards. So mv square by r, mg, and the tension T acting such that it's at an angle theta with the vertical. This is the equilibrium in the rotating frame. The bob is at rest in the rotating frame of the car. Is the concept clear for the free body diagram, people?
Yes.
Okay. So now you can just resolve tension and see how the components balance. So the sine component of tension balances mv square by r. The cos component balances mg. So you can just take the ratio of these two equations. So tan theta is v square by gr. From that you can see your theta will be, and then substitute the values. Now when you are substituting the values, don't forget to convert to SI units. Okay? So a speed of 36 kilometers per hour should become 10 meters per second, and the radius is given G, you take as 9.8 or 10, whatever. Okay, next, any other question from HCV?
Yes, sir.
Sir, 11th and 12th.
11th and 12th, okay, and also question number 15, 17, and 19. Okay, so let's. Okay, so we are doing all these questions next.
Sir, 18th also.
Sir, 29 and 30.
Okay, so let's move ahead with the 11th question. So ceiling fan is given, the blade's diameter is given to you of radius of 120 centimeters, and the rate of rotation is given at full speed in terms of RPM, that is rounds per minute. Okay. So you have to consider a particle which is kind of sticking to the blade of the ceiling fan while it is rotating at this maximum speed, and the mass of the particle is given to you, and it's at the outer end of the blade, so you know the radius of curvature. So how much force does it experience when the fan runs at full speed, and who exerts this force? Okay. So when we talk about how much force, it means we're talking about the net force experienced by that particle, obviously in the inertial frame or in the ground frame. So that net force will be according to its acceleration, and because that particle is sticking to the blade of the fan, okay, it will be in a state of motion which is uniform circular motion, so its acceleration will be purely centripetal. So hope this point is clear. So if this is the side view of the blade of the fan, it's rotating at some particular angular speed at its full speed, and you have that particle sitting over here. Okay, so it's at some distance r like this. So now we are looking at the inertial frame free body diagram. Okay, so it has a centripetal acceleration. Now that is obviously provided by friction. Okay. So normal reaction balances the weight. Friction provides the centripetal acceleration. So the net force that is acting on it, which is mass into acceleration, in this case is mass into centripetal acceleration. So that net force is nothing but the static friction, and it is equal to m omega square r in magnitude. So this is the net force. Okay. Now omega you will have to convert here. It is given in terms of RPM or rounds per minute. So it's 1500 RPM. So that means it is doing 1500 into 2 pi radians but per minute. So divided by 60, and we get the angular speed in radians per second. So as you can see, that is becoming how much now?
50 pi.
50 pi radians per second. And r is given to us as 120 centimeters. So and while doing the calculation, you can use an approximation that pi square is nearly equal to 10. So you will get a approximate answer using this. Okay, so that's question 11. Let's move on to question 12 after this. Similar kind of situation, but now this time instead of a particle on a the same blade of a fan, you have a mosquito which is sitting on a disc, an LP record disc which is rotating. Again, its rate of rotation is given in RPM, and the distance of the mosquito from the center of the turntable is given as 10 centimeters. So frictional coefficient has to be greater than this. So we will prove that condition for limiting friction by taking into account that friction has to, either you can draw the free body diagram in the frame of the disc, in which case you will say friction balances centrifugal force, or you can make the diagram in the free body diagram in the ground frame, in which case you will say that friction provides the centripetal acceleration. Whichever thing you choose to do.
So,
Yes.
sir, in the 11th one,
Yes.
it is not only asking the net force,
Yes.
but it is also asking the force which is exerted on the blade along its surface.
Yeah. So that is only the frictional force. Huh? The particle sticks to the blade because there is some kind of frictional force or some kind of adhesive force, depending on how it is stuck. Okay, if it's just stuck because of friction,
Yes, sir.
It's
whereas
equal to
if
what
there is
we
some,
get.
if there's some adhesive that is applied over there, something which is making it stick due to some kind of chemical bonding, then we'll say it's an adhesive force. But it will be similar to friction, how it acts, right?
Yes, sir.
Understood? Huh? Okay. Okay. Now in this question, in the 12th one, it's Very simple. It's a mosquito which is sitting on the turntable. So obviously, if it is not slipping off, there has to be enough static friction. So the condition for its equilibrium with respect to the disk, which is the rotating frame, is that static friction has to balance the centrifugal force. And that will give us the condition on coefficient of friction. Static friction has to balance the centrifugal force. Okay. And normal reaction will be equal to weight. So from that, we will apply the limiting condition on friction. Right? And from that, we will be able to calculate the minimum coefficient of friction required. So limiting condition friction is that this should not exceed mu n. So from equation 1, the static friction required is equal to the centrifugal force in magnitude. So it's m omega square r. And that should be less than equal to the limiting friction, which is mu mg. So mu should be greater than equal to omega square r by g. Now again, in this omega is 33 and 1 by 3 rpm. Okay, so that is 100 by 3 into 2 pi by 60. When you convert it to radians per second, r is given to us as 10 centimeters, so 0.1 meters, okay. And g you take as 10 meters per second square. So you will get the condition on mu by substituting these values. So this time I have made the free body diagram in the rotating frame instead of the ground frame. So I have used the equilibrium condition in the rotating frame. So for me, static friction is balancing centrifugal force. Right. So this is also clear. Okay. Let's move on to 15th question next. Okay, I'll scroll up. Yeah, while you are going through these solutions, also take a look at question number 15 and 17 next. We'll discuss those two. Okay, so let's go through question 15. It's now based on the language of 14. So again, we have a situation of a simple pendulum. Okay, mass, length of the pendulum, all these are given. Now the speed at the lowest point is given. So we have to find the tension in the string at this instant when it's at the lowest point. That was the 14th question. That I guess you have done. Now it's saying that suppose in the previous problem, the speed is 1.4 again, but when the string is at a very small angle of 0.2 radians with the vertical. So for an angle of 0.2 radians, we have to use the small angle approximations that cos theta can be approximated as 1 minus theta square by 2 and sine theta can be approximated as theta. So I'll just explain these approximations first to you, then we'll move on to it. Okay. So small angle trigonometric approximations. In general, we know that if you compare the definition of angle itself with respect to trigonometric operators applied on the angle, then basically in terms of geometry, we are trying to do something like this. Using a radius r, if we trace an arc which is of arc length s, then the angle is simply defined as the ratio of arc upon radius. Okay, but also if we drop a perpendicular from this and make a right angle triangle out of this diagram, where this is the perpendicular, this is the base, then the trigonometric operators applied to this angle, as you know, are simply defined as these ratios: perpendicular upon hypotenuse for sine, perpendicular upon base for tan, right? And base upon hypotenuse for cos. Okay? So now logically what happens is that for theta being a very small angle in radians, of course, this angle is expressed in radians. So for theta being a small angle in radians, for example, if we take theta something like 0.05 radians, it's a very small angle. Okay, then our diagram starts to look something like this. The angle is very small, so we're looking at a very small arc length in comparison to the radius. So when we drop the perpendicular also, we'll see that the perpendicular is very small in comparison to the base and all that. So what happens is that our theta, sine theta, which is perpendicular upon radius, it tends to become equal to theta, because the perpendicular tends to be equal to the arc length. And similarly, tan theta, which is perpendicular upon base, this also tends to become theta, because the perpendicular is tending to the arc length and the base is tending to the radius. And cos theta actually tends to become 1. Okay. But in this approximation, a more accurate value of cos theta can be determined as 1 minus theta square by 2. So this formula comes from another analysis of the cos, sine function, etc., which I will not get into here, but this comes from something called the Maclaurin series, which you will study in mathematics later, or the concept of power series. Okay, so I won't get into that, but cos theta can be approximated for this for small theta. Okay. So in this particular question, question number 15, they've asked us to specifically use this to determine the value of cos theta, and specifically use this to determine the value of sine theta. Sine theta is approximately theta. So this and this we have to use in this particular questions. Together, these three equations or these three approximations, they are called the small angle approximations. For the three trigonometric functions or operators sine, cos, and tan. But remember here, theta should be expressed in radians. Should not be expressed in degrees. They should be substituted in radians. Okay, so for example, if I tell you that theta is equal to 0.01 radians, find sine theta, cos theta, and tan theta. So your answer will immediately be that sine theta is approximately theta only, which will be 0.01. Tan theta will also be in small angle approximation. But cos theta will be 1 minus theta square by 2, which in this case will be
10 raised to minus 1.
yes 0.00005 in this case. So this is divided by 2. 10 raised to minus 4 divided by 2. So you can see it's almost equal to 1 only. It's 0.99995, right? Cos theta will be like this. This is as good as 1 in this case because so this is an example of the application of the small angle approximation. Okay, so this is something that is going to be pretty significant and useful for us in various parts of physics, making use of the small angle approximations for the three primary trigonometric functions or operators. You can just make a side note of this and then we'll see how we'll apply this in the particular question number 15. So in question 15, in addition to this approximation, we have to obviously make the free body diagram. And now that you have done vertical circular motion, you'll understand it even better. Okay. So as you've seen in vertical circular motion, the combination of tension and the radial component of mg provides the centripetal acceleration, whereas the tangential component of mg provides the tangential acceleration of the vertical circular motion. So that concept only we have to apply to that particular situation or the values in 15th question. Okay. So just go through it and try to apply this yourself. We'll discuss in a minute. Okay, so let's understand this question 15. So the speed of the bob is given as 1.4, which is actually nearly √2 meters per second. When it is at an angle of 0.2 radians with a vertical, we have to find the tension at this particular instant. So we will actually just need cos theta. We will not even need sin theta.
Sir, we will need sin theta for the radius,
And-
like distance.
For the tangential acceleration, right? We will. No, this is not a conical pendulum. You're understanding the point? No? It's not a conical pendulum, so it's a pendulum which is oscillating like this in a vertical plane. You understanding, no?
Yes, sir.
So the circular motion is happening in this vertical plane about this point where the string is attached. The length of the string is equal to the radius. Huh? Okay, so the length of the string is given to us as 1 meter, right? Mass is given as 100 grams. Okay. Now what is given to us in this part is that when this angle theta is 0.02 radians, is it, or is it 0.2? No, 0.2 radians. Okay. So even that we'll consider as a small angle, though actually it's not that small, it's 1/5, but still it's okay enough for the approximation. Okay. So when theta is equal to 0.2 radians, the speed of the bob, speed could be in either direction. I'm just assuming it's in this direction right now. It could be in this opposite direction also. So speed at that moment is 1.4 meters per second. So we have to find the tension in the rope at that instant. So we'll just use the normal dynamics that T minus mg cos theta is equal to mv square by n. Okay. And of course, mg sin theta is providing the tangential deceleration. In this case, it is minus dv by dt. So that's why I said in this particular question, we'll not need sin theta because they've not asked for the tangential deceleration. They've asked to find the tension. So from equation 1, we can see that the tension will be the combination of mg cos theta plus mv square by L. Okay. Mass of the particle is given as take it as 0.1 kg. G will take it as 10 meters per second square. So this is becoming 1 into now cos theta. We'll use the approximation. So 0.98. Right, this is correct. Theta square by 2, that will become 0.02. Yes.
Yes.
So mg cos theta वाला term कितना हो जाएगा? It will become 1 into 0.98 plus mv square by r. This term will be mass into v, which is 1.4 square divided by r, which is
1.
L was how much now?
1 meter.
1 meter.
So 1.
0.196.
So this is 0.98 plus. So 1.4 square is how much?
1.9.
1.96.
1.96.
This will become 1.96. So this will be the tension in
So
Newton.
there's a 0.1.
Yes. Yes, tell me people what is
So it
the
should be 0.196, right?
yes 0.196. Okay. It's 1.96 into 0.1. So 0.196. Correct. So how much is the final answer we are getting?
1.706.
1.176.
Okay, so this should be answer in newtons. Provided g has to be taken as 10 meters per second square. In case it's little less than this, that means you take g as 9.8. Anyhow, so hope the the concept of the question is clear, right?
Yes.
Yes, sir.
Next, what we're doing 17th question, is it?
Yeah.
Okay. You can just take this down.
So,
Okay, 17th question, person stands on a spring balance at the equator. Okay, by what fraction is the balance reading less than his true weight? Okay, so this is again a very interesting concept that if you are standing at different latitudes like equator or Tropic of Capricorn or further up and all that, there will be some small percentage change in the measured weight of a person because the centrifugal force will interfere with the measurement of weight. You are measuring your weight as some kind of, either if you are hanging from a spring balance, then it's basically measuring your weight by uh, measuring the amount of tension in the spring. Okay. Or if you're standing on a weighing machine, for example, so again that weighing machine's surface is loaded on springs, and the surface is applying some kind of normal contact force, which ideally should be balancing your weight. But in the case of a non-inertial frame, it will balance what is called your apparent weight. So the centrifugal force is going to affect your apparent weight. Okay, so that is why just like if you measure your weight inside an elevator which is having a significant amount of acceleration, there can be a significant change in the measured value of weight, like you've seen that in Newton's laws of motion. So similarly, there is actually a small percentage change or percentage error, you can say, in the measured value of weight on account of the rotation of the earth, which applies the pseudo force or centrifugal force. Now we just have to understand like how this force works in terms of both magnitude and direction, depending on where on the earth we are standing. And where on the earth, I need to say what is the latitude. Longitude will not make so much difference. Okay. Because the latitude will tell us how much the radius of curvature is with respect to the axis of rotation. So for example, if you're right at the poles, there will be hardly any centrifugal force acting on you. But if you're at the equator, the centrifugal force will be maximum. Okay, so this error in the measured value of weight due to centrifugal force is going to be maximum at the equator and minimum at the poles. So this is something that we will also later look at in the chapter of gravitation. So we'll come to the second part also, but the first part will show us that actually it's a very small percentage error. So it actually can be ignored because the radius of the earth is so huge and the time period is only 24 hours. Let me explain. So if we consider this as the axis of rotation of the earth is rotating at an angular speed of one revolution in 24 hours. Okay, so if you convert this, the angular speed in radians per second. So now for a person who's standing on the equator, so in the frame of the earth, okay, there is centrifugal force acting on him, which is equal to his mass into omega square into r, where r is the radius of the earth. So that's approximately 6,400 kilometers. The question might not have given you the value, but it's a standard thing you can look up. Okay. In some of the questions in HC Verma, some of the standard constants are not given because just expects you to look it up from some reference table. Okay.
Can you can you again tell us what is the 2 pi by 24?
2 pi by 24. Now see, Earth's rate of rotation is basically what? It completes one revolution in 24 hours, right? The duration of a day.
Yes, sir.
So what is the angular speed therefore? It is the number of radians covered in one revolution, which is 2 pi radians, right? Divided by time period.
Yes, sir.
Understanding, we are just using the concept of uniform circular motion. That the uniform circular motion is a periodic motion which has a time period of 2 pi upon omega, no? Or angular speed is 2 pi upon time period. In the case of the Earth, the time period is one full day, which is 24 hours.
Yes, sir.
Okay, so that's how we now convert it to radians per second, okay, which is the SI unit. Okay. And this will become similarly 6.4 into 10 raised power 3 plus 2, so that's 5 meters, right? So the centrifugal force acting on a person will be this much. So compare that to his weight. The true weight is mg, but what will end up happening is that if he's standing on a weighing machine, for example, the weighing machine will read his normal reaction. So the normal reaction in this case will be mg minus the centrifugal force, and this will be the reading of the weighing machine. The weighing machine will read the normal reaction as mass into g. So m prime will be less than the true mass. Okay. In fact, there is a technical flaw when we say that the weighing machine is reading your weight in so many kgs. It's actually reading your mass in that many kgs. It's expressing your weight divided by acceleration due to gravity in kgs instead of expressing the true weight in newtons. Okay, so anyhow, let's see what kind of difference we get actually over here. So this will be 10 minus, or let's write it like this, g minus omega square r. Okay, now as I was telling you, this omega square r term is actually very small compared to g. The omega square r term is to do this calculation. Be 6. So I'm just doing a rough calculation of this. So I'm getting something like this. 1.08 into 10 raised power minus 3. Okay, this is the value of omega square r. And g is, even if you take it as 9.8, you can see the percentage error is very small, no? Because this factor is very small compared to g. So if I ask you by what factor is his weight less, okay, now you can see that the measured weight is this, okay, whereas his true weight, so by what factor it is less? Factor by which
mg minus mu square
yes,
m mu square by
less
g.
than true weight, yeah. So that will basically be mg minus m prime g divided by mg. So it's basically g minus g prime by g. So you see it's basically omega square r by g. So that is a factor like this. So it's almost a factor of about 1 into 10 raised power minus 4. Let's see what is given as the answer. 17th question. Okay, so its answer is a little different. So I might have made some calculation.
Sir, I guess that was pi square. You took it just pi.
Oh, okay, okay. So I missed one this thing. Yes, yes, you're correct. This is pi square. So I have multiplied
sir,
this by a
like
factor of
pi.
3.14. So that 1.08 when I multiply it by 3.14, Yeah, it will give us about 3.39 instead of this. Now I think we'll get the correct answer, right?
Yes, sir.
Yeah, so this will give us about 3.5 into 10 raised power minus 4. Wait a second, just need to check this once. Pi square 0.4 divided by 144 divided by
Sir,
3.6 square. Yes. It's giving us about 3.39 or 38 into 10 raised power minus 2.
sir, we have to take means 6.4 into 10 to the power 6. No?
Is it? $6,400 kilometers. Yes, yes. Okay, so this is
10 to the power 6 and we
that's
get the answer.
okay. Good. So now you get the. So just make this correction here. This factor will just cancel out. You get this as 10 raised power minus 2 now. No? You get this as 10 raised power. Right. So little bit of patience is required in these type of questions for doing the calculations and all. Okay, so this is the factor. Okay, you can say you can say it is by 0.035% difference. You convert this fraction into okay. So there's a 0.035% difference between true weight and apparent weight. Percentage error in measured weight. Okay. So now I think you can handle the second part of the question yourself, that now you are assuming that you have a different rate of rotation for the earth. Okay. Or different radius. So if the speed of the earth's rotation is increased by such an amount that the balance reading is half the true weight. So that means you want your omega square r to become how much? You want it to become g by 2.
Sir, actually the second part is only the problem. It is asking the number of days, means the length of the day.
Sorry, the second part is asking
The length of the day, but sir, how to calculate that?
I'll tell you. So what you do is now in the second part you assume that the rate of rotation has changed from omega to some new value omega prime. Okay, so that your apparent g has become g by 2, right? So the condition for this is what, that your omega prime square r should be equal to g by 2. Okay, na?
Yes.
Because see, what is your mg prime? Your mg prime is your true weight minus the centrifugal force. No? So now your centrifugal force is omega prime square r. So if you want g prime to be g by 2, that means you want this factor to be half the true weight,
Yes.
right? So you solve this now and find the value of omega prime, and now equate that omega prime as 2 pi upon new time period. Understood? No?
Yes, sir.
So you get how the duration of the day has changed. In fact, you can even relate it like this, that omega upon omega prime is 2 pi upon 24 hours divided by the new time period. You can do it like this. So once you found your omega prime, you can find the new time period or the new duration of a day like this. Okay. So we'll see that you'll have to significantly speed up the Earth's rotation. So the duration of a day will significantly have to go down. Okay, so according to the answer, it's saying that it should be about 2 hours instead of 24 hours. It's a factor of 1 by 12. Okay, so I'm assuming we can complete this problem, people.
Yes.
Okay, let's come to 19th question. So 19th question, in fact, is also a situation where a body is in vertical circular motion, but this time it is a body which is, it can propel itself or it can apply brakes. So it is doing a uniform circular motion at constant speed. So what is the maximum velocity that it can, for which it can be in contact with the road at the highest point? So just make the free body diagram of the road at the highest point and all that. Okay, so let's go through the question first. Motorcycle has to move at constant speed on an overbridge which is in the form of a circular arc. So it starts from the highest point. So what is the maximum speed with which it can start so that it does not lose contact right away at the point at which it starts? Okay. Then the second part, if it instead of going at that particular speed, it goes at 1 by root 2 times that speed, then what is the point at which it will lose contact? Where it will lose contact means we can find the angular position of the point at which it will lose contact. Okay. And finally, if it does not lose contact anywhere on the bridge. Okay, so let me explain the question with a visual picture. Okay, so let's say the overbridge is a circular arc like this. The total length of the arc is L, okay, and it has a radius of curvature. So if we drop a normal from the two endpoints and a normal from any other point, including the top point, will all intersect at the center of curvature here. Okay, so this is R. So if we take this angle on this side, for example, as beta, because it's symmetrical, this 2 beta is the total angle, so it will be L by R. So this is the first relation we have to understand, okay, that angle is equal to R upon radius. So we have to make use of this. Okay. Now we can represent our motorcycle as a particle in our free body diagram. So if that starts off with a speed, let's say V0 or whatever at the top. Okay. Then when it starts with this speed V0, immediately, because it's on a circular path, so what will happen is that there will be, it has to have a centripetal acceleration to maintain that circular path. So if you don't want the motorcycle to jump off, we want it to remain in contact. Okay, so it should, if it's remaining in contact, this normal reaction should be non-zero. So the condition for normal reaction to be non-zero is that it should have the required centripetal acceleration so that it can continue like this. So we want this equation. It should go at a uniform speed v. So at the top point, at time t equal to 0, okay, mg minus n is equal to mv square by r. So the normal reaction at the top is mg minus mv square by r at the top. In fact, let's write this as n naught so that we understand it's the normal reaction at the top. So for contact to be maintained, n naught should be greater than equal to 0. That means actually it should be greater than. Equal to 0 also means it's lost contact just about. So V should be less than root GR. That's the answer to your first one. Okay, what can be the maximum velocity for which the contact with the road is not broken at the highest point? It should be such that it's slightly less than root GR. Now let's come to the second part. So in the first part, it's almost equal to root GR. It should be slightly less than this one. Okay, now in the second part, instead of this speed, at the top we are giving it a speed of that V max that we have calculated divided by root 2. So that is root GR by 2. So you will see, therefore, this translates to the fact that at the top, the normal reaction will now become, you will see, half the weight, because this V square is now GR by 2. So mv square by r becomes like this. So the normal reaction will be half the weight in this case at the top. Okay. But at any other position, so at some time t, when the angle is theta, the angular position theta, if you look at the free body diagram at such an instant now, you see that if it has not lost contact, normal reaction is acting like this, mg is acting like this, it's moving at a uniform speed v. So there also has to be braking that it does to avoid increasing speed. So there has to be, to avoid slipping or acceleration, it has to do this. So tangential acceleration is 0, means mg sine theta has to be balanced by friction, and centripetal acceleration is v square by r. So that means mg cos theta minus n is equal to mv square by r. So these are the two dynamical equations at any angle theta. So use these now to understand this part, that at what position is going to lose contact if the speed at the top is root gr by 2. Okay, so anybody got the answer? For the second part, what is the angular position at which it will lose contact? Let's say somewhere here, if it is losing contact. The condition for losing contact is that normal contact force should become 0. So this V is equal to root GR by 2. Okay. So we want to find the particular angle theta at which the normal contact force becomes 0. So at that moment, there should be only mg acting. Okay. And actually friction will also become 0, but we just write it like this. Okay. It won't be possible to generate friction actually at the moment when normal reaction becomes 0, because obviously this will also no contact force, so there's no friction you can get. Anyway, so the condition for n to be 0 is that mg cos theta should be equal to mv square. So theta you can see will become cos inverse of 1 by 2 or pi by 3, that is 60 degrees. So at the top, it's starting off with a speed of v equal to root gr by 2 and maintaining this uniform circular motion. Then it loses contact. The surface at this particular angle. All right, people. So that was the discussion of the 19th question. Okay, now the last part of the question, we also want to find the value of V so that it does not lose contact anywhere on the bridge. So if it does not lose contact anywhere on the bridge, it should not lose contact at the lowest point, which we had seen was at some kind of an angle beta, which we had written as L by 2R. So as you're going further and further away from the top point, your normal reaction is becoming lesser and lesser in general. So if it's starting with the speed v here and reaching all the way here, the speed v, then the condition for it to not lose contact is that at this angle beta also, the normal reaction should be greater than equal to 0. So at theta equal to beta, if n is greater than equal to 0, that means it does not lose contact.
Greater than, right?
Yeah, I mean just about at that point, if it's losing contact is fine because it's reached the end of the overbridge.
Okay, yeah.
It's like a limiting condition. Okay.
Yes.
So now remember that beta was L by 2R. So A to B, where A is this point and B is this point. So the condition for this to happen is that in general. So n should be greater than equal to 0 at theta equal to beta. So mg cos beta minus mv square by r should be greater than equal to 0. So that will tell us the limiting value of v, that v should be less than equal to root gr cos beta, where beta is L by 2r. So the maximum speed at which we can do it is
Sir, can you just go back for a second?
yeah. Okay, done.
Sir,
Yes.
Yeah.
sir, it is given behind that for the part B, the answer is a distance pi r divided by 3 along the bridge from the highest point.
Because
That's
see,
the
the angular position is pi by 3. No? What is the distance? Is the arc length. No?
Yeah,
Yes.
sir. Got it.
So just arc length will be how much? Radius into distance.
Yes, sir.
Okay, so just multiply that angle of pi by 3 with the radius. So you'll get the distance along that arc, how far it reaches before it loses contact, right?
Yes.
Okay. So that completes this set of doubts. Now, what we'll do is we'll also do some more examples of vertical circular motion. Okay, what we were seeing in the last lecture, so that you can also in this remaining like time before the next lecture, do the questions which are there in the next chapter, like but related to circular motion. That is vertical circular motion questions from work by energy chapter of HC Verma. So for that, we'll just look at a couple of more example type of situations. So last time we were looking at vertical circular motion of a particle attached to a light thread. Okay. Of a particle attached to a light thread.
Sir,
Yes.
sir, the 18th question was left, sir.
Okay, we'll come back to 18th also. Just
Okay,
let's
sir.
do an example of this, then we'll come back to 18th. Okay. So let's say this is the vertical circular path along which such a particle is moving, which is attached to a thread of length L, and that thread is attached to some point O so that it can rotate freely about that. So if it is given at the lowest point, a speed V0 like this, and what we had seen in the last section was that the tension to begin with at the lowest point is such that tension minus weight is equal to mv square by r. So the tension is equal to mg plus mv naught square by L at the lowest point. Okay. Now compare that to when the particle reaches some angular theta like this, where theta is less than 90 degrees. Okay. So when it reaches some angular position theta like this, so by now the speed of the particle would have reduced to some v. Okay. And the tension also we saw will reduce as you go up, as the angle theta changes. So we had seen that we can write two equations here. One is the work energy relation and the other is the dynamical equation. The standard method is we express that height h. For this point, we see that half mv square, that is the kinetic energy at this point, is the kinetic energy at the bottom, which is half mv naught square, minus the gain in potential energy. So V is equal to square root of V naught square minus 2gh, where h here becomes L into 1 minus cos theta. This was one equation. And the other thing we saw is that for dynamics, you can see that T minus mg cos theta is equal to mv square by L. So T at any point is becoming mg cos theta plus mv square by L. And mg sin theta is providing the tangential acceleration. So the tangential acceleration is actually minus dv by dt. It's a deceleration, which becomes g sin theta. So these are the dynamical equations. So particularly this is the equation of importance. Now from equation 2, you can see that if V naught is small and V becomes 0 at some theta less than 90 degrees, then the particle momentarily stops. Okay, but the tension is non-zero at that point, because tension is equal to mg cos theta if V becomes 0 at some point. So the string remains tight. Okay. So this is just a quick recap of what we have understood in the last question. So if the particle is given sufficient amount of speed V naught, it will not stop before reaching 90 degrees. But on the other hand, if the speed is comparatively less, then it will never reach the 90-degree position, let alone cross that and complete the vertical circular motion. It will stop at some theta less than 90. So now we can find a limiting condition, that what is the minimum speed we have to give so that it crosses the 90-degree position. That we will understand from equation 1. So from this we can further see that condition for the particle to stop before theta is equal to 90 degrees, that V should be 0 at theta less than 90 degrees. So that means V naught square minus 2gl 1 minus cos theta should be equal to 0 at theta less than 90 degrees. That will give us the condition that means V naught square should become less than 2gl, or we should give an initial speed at the bottom which is less than root 2gl, not equal to but less than. So this is the condition for it to stop before it reaches the 90-degree position. This is the condition for the particle to stop at theta less than 90 degrees. So it acts like a pendulum. Now, on the other hand, from this we can also understand if V naught is greater than root 2gl, okay, it will cross theta equal to 90-degree position. And from there on, what might happen is it may complete the vertical circular motion. Okay. Or on the other hand, the string may become slack and it's not able to complete vertical circular motion. So again, one of two possibilities occurs, and which one of the two occurs again depends on the value of V naught, that how much greater than root 2gl it is. If it is quite a bit greater, then it will have enough momentum to complete the vertical circular motion. But if it is only slightly greater than root 2gl, and we'll see by slightly greater what I mean in terms of value exactly. But if it is slightly greater but not too much greater than root 2gl, then it won't have enough momentum, and therefore it will not be able to complete the vertical circular motion. Before it, reaches the highest point, at some point in between, the thread will slacken and the particle will fall off into a projectile motion. It will not be able to continue in vertical circular motion. Okay. So this condition is very important to understand, which is why I'm discussing it in detail. Just go through it carefully. Then we'll develop the values. Okay. So right now, one critical value we have found out is the root 2 GL thing. That if the initial speed at the bottom is less than root 2 GL, then it acts like a pendulum. It stops at some point where the angle is acute, comes back, goes to the other side to the same theta, and back and forth, back and forth. So it behaves like a pendulum where the maximum angular displacement is less than 90 degrees. But on the other hand, if we give an initial speed at the bottom more than root 2 GL, then it's not going to behave like a pendulum. It's going to either complete the vertical circular motion if it has enough momentum and enough energy, or it's going to slacken off. The thread is going to lose its tension and it's going to completely go out of the circular path and fall into a projectile path. But that will happen at some theta after 90 degrees. Okay, so now let us understand this question, this condition in more detail. To answer your question, Vedant, actually whether it slackens or it completes the vertical circular motion actually all depends on the initial velocity and its relationship with L. It does not depend on the mass of the bomb. Okay? Because both kinetic energy and gravitational potential energy are proportional to mass. So we'll see ultimately mass does not play a role. What plays a role is the relationship between V naught and L. Just like we've already got this relation of root 2 GL. That is the condition for whether it crosses 90 degrees or not. Like that, we'll get another condition. Okay. So now for V naught greater than root 2 GL, okay, the particle crosses the theta equal to 90 degree position. Now at some theta greater than 90 degrees, let's look at the free body diagram. Okay. And understand what I'm talking about, that how this can happen, that instead of continuing and completing the vertical circular motion, how it can easily happen that if the particle does not have enough kinetic energy, enough speed, this thread will slacken off. Okay. So if I'm now gone to some position like this, where my angular displacement from the initial point at the bottom is greater than 90 degrees. So of course, the speed will continue to decrease even after you go past 90 degrees because, okay, the speed will continue to decrease because your gravitational potential energy is continuing to increase. The particle is gaining height, so it has to lose kinetic energy. Okay, but in addition now, the relationship between tension and mg changes somewhat. And that's what makes things very interesting. So here at the bottom, the speed was V naught. Now by the time it's reached here, now this V naught was greater than root 2 GL. We've assumed that. So it's crossed the 90 degree position, and now somewhere here, at some kind of an obtuse angular displacement theta, let's say the speed has become V. So first of all, we can see that the relationship between V and V naught will come from work energy, where this is the total height it has gained. Okay. Now, because theta is an obtuse angle, we'll just express it in terms of its complement, which is beta over here. So if the length of the string is L, you can see that this part here is L cos beta. So this is L. So H is equal to L1 plus cos beta, okay, where theta is equal to 180 minus beta. So we have half mv square is again equal to the initial kinetic energy minus the gain in potential energy. So we have P is equal to square root of V naught square minus 2gh, or so this is our conservation of energy or work energy relation, which gives us V as a function of theta. In this case, theta is equal to 180 minus beta. Now let's come to the free body diagram. So the free body diagram is the interesting thing here. The tension acts like this and mg acts like this. And this angle is again beta. Okay. So when you look at the free body diagram carefully, now you realize that there's a difference between how tension was acting with respect to weight earlier on when theta was less than 90, and in this situation when theta is greater than 90. And that difference is that mg has a cos component which is centripetal. Earlier it was away from the center, but now it's pointing towards the center. Okay, so the particle going at the speed v, the equation becomes p plus mg cos beta is equal to mv square by L. So what this is showing us is that tension is equal to mv square by L minus mg cos beta instead of plus mg cos theta. Okay. So this second equation now shows us that it's possible that if our speed is too small at a particular position, then mv square by L gets cancelled by mg cos beta and tension becomes 0. So this shows us that T becomes 0 if mv square by L is equal to mg cos beta at theta equal to 180 minus beta. So if this condition is satisfied, the string can slacken off. This is the condition for the thread or the string to slacken. So if we want to complete the vertical circular motion, we should give initial speed such that this condition does not happen. So as you can see, the value of V is getting smaller and smaller as you're going up, as your theta is increasing. But how small it is also depends on how much V naught is. If your V naught is comparatively large, even though your V is decreasing, it will never become so small that mv square by L is cancelled by mg cos beta. So your tension will not become 0. Your string will always remain tight. But on the other hand, if your V naught is not so large, it's larger than root 2 GL, but not so much larger, that at some point what is happening, the condition for T2 becomes 0 is getting satisfied. That is mv square by L is getting cancelled by mg cos beta because the V is comparatively small. So then what will happen? The string will lose its tightness and it will not be able to provide centripetal acceleration and all that. So the particle will go into a projectile path and fall off from the circular path.
Sir,
Sir,
Okay, so people, now let's understand the condition for the string to slacken is this, that tension is
So,
zero at some point. Okay. Yeah, tell me.
so what will happen if theta goes to 180 degrees?
So let's understand ना कि theta equal to 180 अगर पहुंच रहा है ना, the condition is that the tension should not have become zero at any point before that. ना? Okay.
sir.
So for the particle, on the other hand, to reach the highest point, the highest point is theta equal to 180 degrees. Okay. So
Yes.
tension should be non-zero at all theta from 0 to 180 degrees. It should not have become zero before that. So that means tension should be greater than equal to, just about equal to zero is also okay, but greater than equal to zero at theta equal to 180. That becomes like the limiting condition. Because what is happening now, as you're going up, your tension is decreasing more and more. So agar highest point pe you have ensured that your tension is greater than equal to zero, then at any other point before that, it will anyway be greater than zero or non-zero. Understood now?
So, sir, at
Yes, sir.
180 degrees, will the thing, means the particle, will fall down due to mg force?
No, that is the point. Na? If it has reached that point with the string being tight, that means it has enough momentum to carry it through. Okay. So we want the free body diagram at the highest point to be like this, that there is some tension in the thread. The thread is not slackened. So why that is possible that the thread is not slackened even though mg is acting on it? Because there is enough centripetal force required, no, to keep the particle turning. You understanding? No?
There is a like tangential acceleration there.
Yes.
You mean to say? Okay.
So what is happening at the highest point? I want tension to be greater than equal to zero. So P plus mg should be equal to mv square by L, and T should be greater than equal to zero. That means mv square by L should be greater than equal to mg, or the speed at the highest point should be greater than equal to root gm. This is the condition, that I should give enough kinetic energy at the bottom so that it reaches the top. It can reach the top with a speed greater than equal to root gm. If I've ensured that, then I've ensured that the string is always tight. So it's always remaining in that circular path. The string is not slackening. Okay. So this is the condition on V at the top, that is theta equal to 180 degrees, for a vertical circular motion to be complete. If an object or a particle is completing vertical circular motion, then when it reaches the top, it has a speed of greater than equal to root gm. Okay, so now what about the condition on V naught? So you can see that at the lowest point, compare that with the highest point. The height difference is how much? The height difference is 2L.
Oh,
So the relationship between these two is that V square is equal to V naught square minus 4gm. Okay, so now V square is greater than equal to GL, means that V naught square minus 4gl should be greater than equal to GL. So that gives me the condition on the speed at the lowest point. How much minimum speed I have to give if I want to guarantee that it completes vertical circular motion? The thread should not slacken in between. I have to give a minimum speed of root 5 GL or more than that. Okay. So this is the critical condition for completion of vertical circular motion. This is the critical condition to complete. So now we can understand that there is a whole set of values. If the speed at the lowest point is less than root 2 GL, it acts like a pendulum. Okay. The maximum angular displacement you reach is less than 90 degrees, and V becomes 0 at that maximum angular displacement. But tension is non-zero at that point. The string does not slacken. If V naught is greater than root 2 GL, but less than root 5 GL, then what will happen is that it crosses theta equal to 90 degrees, but at some theta in between 90 and 180, greater than 90 but less than 180, the string slackens. So it does not complete vertical circular motion. And only if our V naught is greater than equal to root 5 GL, this condition now. This is the third situation. Then it completes vertical circular motion. In between these two, you can also take one special case where V naught is exactly equal to root 2 GL. So if that happens now, it again behaves like a pendulum, but it just about reaches that 90-degree position. The maximum theta is not less than 90, it is equal to 90 exactly. Okay. So you need to remember these cases and these special values, root 2 GL and root 5 GL, so that you can, looking at the given value of V naught, comparing it with the length of the thread, you can understand which exact situation is taking place. Is the motion of the particle or object behaving like a pendulum, or is it going to go in circular path and then at some stage the string will slacken and it will fall into a projectile path, or will it be able to complete the vertical circular motion and keep going round and round?
So in second condition where like string slackens in between the motion, so for that the projectile will start with an acceleration, right?
The projectile is, sorry, what?
The projectile motion after the string gets slackened, it will start with an acceleration. No?
नहीं, see, the fact that your tension has become zero, na, string has slackened, that means body पे net force अभी क्या act कर रहा है? Only the weight, right?
Yes, mg. Yes.
So it will have an acceleration of g, na? And that's
Yeah.
why it's a projectile motion. Na? Because projectile motion is motion under the action of gravity.
Yes, sir.
Okay, why it will not straight away fall vertically? Because where the string has lost the tension, na, the particle is having some momentum. You understood? Na? So it becomes like from that point it is projected and moving under the action of gravity. The string doesn't play any role because it's become loose.
Yes, sir.
Okay, so it will not come straight down in a free fall path from where the string loses tension, but it will go into a projectile path where eventually it falls. It's not going to go too much higher and all that. The string will not tighten again. Instead, what will happen is it will fall into a projectile path.
Yes, sir.
So
Yes.
I had one doubt from cumulative test.
You had one doubt in, sorry, what?
Cumulative test, the advanced part.
Hmm. Uh, can you send the
There's a
doubt?
doubt in the diagrams or like.
Okay, can you just send it to me on WhatsApp?
Yes, sir. I'll send it right
Okay,
away.
you have a screenshot or something, just send it to me on
Yes, sir.
WhatsApp.
Yes, sir.
I'll explain. Okay. And in the meantime, we'll also do one numerical problem related to these values. Okay, very important.
So can you just scroll up for a second?
Yeah.
So did you receive my text?
Okay. So now let's look at a numerical example. Yeah, I will take a look at the question you sent also. Okay, so we have a 10-meter long string, and at the bottom we have attached a particle P, which is of mass, let's say 1 kilogram. And we are also taking the value of G as 10 meters per second square. Now we initiate the circular motion, the vertical circular motion, by giving it a horizontal velocity of V0. So in the first case, if V0 is equal to 30 meters per second, okay, show that the particle completes the vertical circular motion. Find the speed at the highest point and also find the maximum and minimum values of tension in the string during the vertical circular motion. Okay, so you have to think when the tension will be maximum, when it will be minimum. Okay. Second case, if V0 is equal to 20 meters per second, okay, show that the thread slackens at some point. Okay. find the angular displacement at the point at which the thread slackens, and also find the speed of the particle at the point at which the thread slackens. So if you already know the analysis, the two critical things, root 2 GL and root 5 GL, and how to relate V naught in different conditions with respect to these two, then you can understand which of the cases is taking place for a given value of V naught, like 30 or 20 or whatever, very easily. And then you have to just get down to applying the two equations that are required. One is the work energy relation and the other is the free body diagram relation. So just try out this question, and I'm just going through the question that you have sent. Two particles A and B are connected by a rigid rod. The rod slides along the perpendicular rails like this. No, the question is complete, beta. Okay, I will give you a hint. This is a calculus problem. Okay, you have to use the condition that the length of the rod remains fixed. You understanding?
Oh, okay.
Okay, so what you do is now you take the corner of the wall and the floor, take that as suppose your origin. So your origin to the point A, suppose that distance is x, and your origin to the point B, that distance is y. Then you have a constraint that x square plus y square is constant, because that's the length of the rod square.
Yes.
Okay, and now the way the points A and B are moving, dx by dt will be equal to the positive velocity
Yes.
of the point A, whereas dy by dt will be negative of the velocity of the point B, because B is coming down. Okay, so differentiate your constraint relation and use chain rule. That x square plus y square constant hai, so rate of change of that whole quantity x square plus y square should be 0.
Okay, yes, understood.
And when you differentiate it using the chain rule, your dx by dt term and dy by dt term, replace them with the relevant velocities va and vb with the proper sign. So you get a relation between va and vb.
Okay.
Okay, so it's an interesting question. Try it out. If you can't get the answer, I'll help you further. You can just message me later. Okay. Now,
Yes, sir.
currently work on this question because this is important. Okay.
Yes.
Hello. Come, hi, sir. Hi, how are you doing? Okay. Just give me Okay, so let's come to this question. Anybody got the answer for the first part?
Yes.
Sir.
To show that it completes vertical circular motion, you just need to compare this value of V naught with what? The critical value root 5 GL.
Yes. Yes,
So
sir.
root 5 GL यहाँ पे कितना होगा? It will be
10
root
root
of 5 into 10 into 10. So 10 root 5. So that will be around 22 point something, not 20 point,
Yes.
22.4 or something. So definitely you can see that V naught equal to 30 meters per second is greater than root 5 GL. So it has to complete vertical circular motion. Okay. So now to find the speed and the tension and all that, so you can see that at the bottom our speed is 30. So by the time it reaches the highest point, if I take the speed as some V, first thing is use your work energy theorem. So this is going through a height of 2L, right? And L is 10 meters.
Yes.
So V is square root of V naught square minus 4GL. So this is becoming 900 minus 400, I think, right? So it's becoming 10 root 5. So in fact, it's having that root 5 GL kind of value, interestingly. Approximately 22.4 meters per second. This is the V at the highest point. Now, once you get this, you can also understand how much the tension is at the highest point, because the FPD will show you, right? Whereas at the bottom, it's a situation like this. So at the highest point, our speed is so much and our tension is such that, so the tension should become mv square by L minus mg. Now we expect the tension should be a positive value, no? Because we've given V more than root 5 GL. And when we substitute, you'll see that that's what's happening. This is 500 by 10 minus 10. When you substitute. Okay. So the tension is in fact the mass which had taken 1 kg into 50 minus 10 or 40 newtons. So it's in fact interestingly more than the weight, because we've given it quite a bit of kinetic energy at the bottom. So it's not only the thread is tight at the top, but it's having a tension more than the weight. Whereas at the bottom, lowest point, the tension is such that T naught minus mg should be equal to mb naught square by m. So T naught is even more. It's in fact the maximum tension of the overall circular motion. This is the maximum tension. So this was, so it's going to be 100 newtons. So now you realize that overall in the entire circular path, this is where the tension is maximum. And this is where the tension will be minimum. Okay, this is understood by people?
Yes.
And same for speed. This speed is the minimum speed, because once it crosses that 180-degree position, again it's going to accelerate as it comes down in the circular path. And by the time it comes down again, it will achieve 30 meters per second. Then again it will decelerate. So this is the minimum speed, and this 30 meters per second is the maximum speed. Maximum speed, maximum tension. That is the property of the lowest point. And minimum speed, minimum tension, that's happening at the highest point. Okay. Now let's come to the second part, where we have changed the value of V naught at the bottom to 20 meters per second. So straight away you can see that this V naught is less than root 5 GL. But at the same time, it is greater than root 2 GL. Because
Sir, can you scroll up, please?
Yeah, this is square root 200 and this is square root 500, whereas this is square root of 400. So it's in between these two. That's also easy way you can compare. You know? Just square the velocity and compare it with 5 GL and 2 GL. Yeah, this part.
Yes.
Yeah.
Sir, sir, we have taken that half mv square is equal to half mv naught square minus mg 2l. So why are we not taking mgl?
So see, basically, how this is coming, we are saying that the final kinetic energy at the top is equal to the initial kinetic energy minus the gain in potential energy, no?
Yes, sir.
Right? So how much height it is going through? How much height it's gaining? Twice the length of the thread, no?
Yeah, sir. So means the length is nothing but the radius for that circular
Yes,
motion.
yes, exactly. The length of the thread is the radius. So now it's going through height which is equal to the diameter, no? From the lowest to highest point.
Yeah,
Hence,
sir.
the value of h in that mgh, we'll substitute h as 2n.
Okay, sir.
Right? H will be 2l from lowest to highest point. Okay, so people, this is understood.
Yes, sir.
Yes,
Okay.
sir.
Okay, so now let's come back to the second part. Okay. So यहाँ पे we understood that if V naught is 20 meters per second, V naught square is 400, which is less than root 5 GL but greater than 2 GL. So it's falling in this category. So what will happen? The string will slacken somewhere. So that theta, let's find out. Okay. So now we also know that that theta will be an obtuse angle. So it's better to find the complement of that. So we'll write this theta as 180 minus this beta eventually. So the usual condition that given the speed V naught here, we can relate it with the speed V at this point. But now we have to find the condition that the string is actually slackened, not tight. Okay. So the tension has become 0 at this point. So the condition for tension to become 0 is that mg cos beta should be equal to mb square by m. So that's our first equation. From this, v square is equal to gl cos beta. Okay. And then we have the work energy relation between this and this. So again, you can see that this is L cos beta. So half mv square is equal to half mv naught square minus mgh, where h will be equal to L into 1 plus cos beta. So from this, we have v square is equal to v naught square minus gl into 1 plus cos beta, this term. Right? So this is our second equation. Now we'll compare these two. And we will get the exact value of beta, and that will indirectly give us theta. So comparing these two, we can see that e square, which is gl cos beta, equal to v naught square minus 2gl 1 plus cos beta. So 3gl cos beta will become v naught square minus 2gl. Now we can put the values. So 3 into 10 into 10 cos beta should be equal to v naught square. So that's 400 minus 2 into 10 into 10. Okay. So 300 cos beta. So I'll just cancel 100 on both sides. Is equal to 400. So that becomes 4 minus 2. So you can see that beta is cos inverse 2 by 3 or cos inverse 0.67. And if I'm not mistaken, that's about 48 degrees. This will be about 48 degrees. Let me just check. So now you know that theta will be 180 minus this beta. So that is the angle at which the string is slackening. Yeah, it's about 48 degrees. That's correct. So theta at this kind of angle, the string slackens, and the speed at that point becomes root gl cos beta. That is,
Sir,
yeah.
sir, I just wanted to confirm the value of m, the mass.
In the problem, the mass was 1 kg.
Okay, sir. Got it.
Okay. Okay, so hope the two conditions are clear now. No? For crossing the 90-degree position, if it's greater than root 2 GL but less than root 5 GL, then this is how we find the position at which the tension becomes 0. On the other hand, if it's greater than root 5 GL or greater than equal to, it completes the vertical circular motion, right?
Yes, sir.
Yes, sir.
Okay, people. So with that, we complete today's session and we complete circular motion with this. Okay, so we will pick up. We'll start working on center of mass in the chapter system of particles in the next lecture. We'll keep some time aside for doubts, discussions as we go along. But we are now in a position to start the next chapter. Okay, people. All the best.
Thank you, sir.
sir.
Bye.
Bye, sir.
Nice.
Sir.